Hi there, thanks for joining us. This is a Q&A edition of Space Nuts. My name is Andrew Dunkley. Coming up, we're going to look at a lot of issues, one involving dark matter. This question, though, comes about as a consequence of someone who wasn't real happy with a discussion we had recently. So we'll certainly reinvestigate that. We'll also look at flawed mathematics. That sounds like my entire school career. We'll also be discussing black holes and gravity and energy in space. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us again to sort all of this out is Professor Fred Watson. Hello, Fred.
Hello, Andrew. Let's get into those questions, eh?
Yes, let's just hit the nail on the head and start. And this first question comes about as a consequence of us answering a previous question. And I think we've kind of put Kevin's nose out of joint just slightly. I might say, though, he's used a word that I think is probably not in keeping with the way you deal with things, Fred. I would never, ever accuse you of being glib. However, that said, Kevin does have issue with the dark matter question. Now, so that I don't mash Kevin's question up, I have prepared it with an AI voice so that it comes out clean and unadulterated, if you like. So let's see what the issue is and see if we can pick it to pieces and put it back together again. This is from Kevin.
In your 428th episode, I was saddened by your response to a listener question asking if space-time itself might be dark matter. I found your emphatic and almost glib no just doesn't fit with your regular open-mindedness. I have asked similar questions before in other forums and received the same dismissive, no, response without any depth of thinking about the question. For starters, we don't yet know what space-time actually is. But, if it can be distorted, it has some aspect of a substance to it. And if it is a form of substance, why should it not be considered as a candidate for dark matter? It is everywhere. It is transparent to EM. It is weakly interacting. It can be distorted, which means what? That it becomes more dense in some areas than others. So what if areas that are denser have a positive gravitational effect compared to average background space? You might see clumping. So what if areas that are less dense have a repulsive gravitational effect compared to average background space? You might see voids. I'm not saying space-time is dark matter, but dark matter is not actually a thing that has been discovered yet. Variable density space-time may be all that is needed to explain the gravitation anomalies that we observed, and I think it deserves a more open-minded level of exploring than a simple dismissal. What I'd like to know is how would you test it as hypothesis? Has anyone done said testing? Has it been exhaustively ruled out? By whom? How did they do that? Otherwise, brilliant show. Kevin from Melbourne.
Okay, Kevin, thank you very much. I hope you don't mind me using AI to put that question out there. I just wanted to make sure it was intact because you obviously are very serious about this issue. And you have had problems in the past getting a straight answer, and you put a lot of thought into it. I give you credit for that. So, Fred, how can we sort of discuss this question with a more robust approach?
By getting somebody who's more of a specialist in dark matter physics and cosmology than me. As a commentator, I mean, what I report on is what I understand from the work of my colleagues who work in this sort of field. And there's certainly nothing I've heard and seen in the literature that would equate dark matter with space-time. It is always regarded as something that exists within space-time. Now, there'll be very good reasons for that, and almost certainly, if some of my friends and colleagues were sitting right here now, they would be able to point us in the right direction as to why that is the case. I haven't checked the details myself, But nobody is making that suggestion. It's almost universally accepted as being a subatomic particle of some kind which exists within space-time that we haven't yet detected. I'm sorry if I sounded glib, but it certainly wouldn't have been my intention. And dismissive isn't something I like to be described as either. Because we normally exactly keep an open mind about many of these issues, and part of that open-mindedness is because I'm not a specialist in the field. I'm reporting on what my colleagues, not just one of them but many of them, are saying. So let's keep it in mind. I will explore it a little bit further. The idea that Geordie's going to get involved as well. There we'll go. I'll explore the reasons why we don't consider it to be part of space-time at a later date.
Okay, no, that's fair enough.
Kevin.
I mean,
thanks for your comments, Kevin.
Yeah, and look, I appreciate his frustration because he's obviously tried to get answers on this and may not have liked the way we approached it at that particular time, but it is an area that is under heavy investigation.
Indeed, yeah. Everybody's looking at it.
Even 1 or 2 episodes ago, we talked about a particular search for dark matter that came up with nothing.
Really?
And that doesn't mean it doesn't exist. In fact, we know it exists. They just haven't found it within certain parameters. And so they'll be looking bigger. But that particular equipment hasn't actually been built yet. So the frustration continues. So we're hopefully not a long way off figuring out dark matter, but right now there's lots more questions than there are answers, and it's I suppose it's a watch this space scenario. But no, we appreciate you passing on your thoughts, Kevin, and hopefully we'll be able to come up with some more information moving forward once we've looked into it through the respective experts. Let's move on to our next question. This comes from Simon, and he says, "Hi, is it possible that the breakdown of models at extremes of the universe is due to our mathematics being flawed rather than the models? For example, fluid dynamic models of real-world scenarios rely on imaginary numbers. Might our system of mathematics be slightly misaligned with the real world?" Thank you, Simon. I think we've kind of talked about the mathematics being off in respect to some things in the past, and even Einstein considers the model of relativity is probably not right, even though we can't prove it wrong. So it is a good question to ask, and the answer is, yeah, probably somewhere along the line the numbers don't stack up.
Yeah, I think it's an interesting, Simon's postulate particularly about imaginary numbers, which is, we call them complex numbers. They have a real and an imaginary component. Why is it imaginary? Because it's the square root of -1, which doesn't exist. But it's an incredibly useful tool in so many fields of science and engineering too. Your aerodynamics relies on imaginary numbers, so it's imaginary numbers that keep your plane in the air. Could that understanding be flawed? Yes, I think it could. And again, I think we are pretty open-minded about this idea. What breaks down our physics in the extreme situations that I think Simon's referring to, things like, how do you deal with the way the universe behaved immediately after the Big Bang, where you've got temperatures and pressures that we've got no physical experience of in terms of working out how they would behave. And they become what we call highly nonlinear. That means that they behave in a way that is actually really hard to predict. And so that's saying that our physical models are not robust enough. Not necessarily that the mathematics is not robust enough, but it is an interesting conjecture. I think Simon's point is well made. Might our system of mathematics be slightly misaligned with the real world? Well, in extreme cases, it probably is when you think about, the temperature immediately after the Big Bang.
Well, yeah, that's a good point. I mean, there's no easy remedy, though, is there?
No. I mean, there are people who are modelling those scenarios where you do have these extremes, and they're probably relying on relatively conventional mathematics, although, yes, they will involve complex numbers and all the rest of it. But I think it gets weirdest, actually. It gets weirder in the quantum world, where we've got all kinds of interesting notions that do rely heavily on mathematics, superposition, entanglement, all of these things. And they rely on particular types of mathematics, Hilbert spaces and things of that sort, which are well understood, I have to say, but to the uneducated, and I include myself in that, because mathematics was my Achilles heel at university, nearly cost me my degree. I think these things look like mathematics gone wrong, if I can put it that way, but they haven't. They're well understood. So the misalignment with the real world, I think it's possible, but in many ways the mathematics is all we've got to rely on, so we just keep plodding on with what we know.
Yeah. You mentioned superposition. I've just finished watching a science fiction series called Dark Matter.
Right.
And the goal of the main character, the scientist that was the whole story was built around, his aim was to achieve superposition so that he could travel interdimensionally. It was brilliantly done. They obviously had to work out how to make it a convincing storyline for those who are so into science fiction and science, for that matter, to make it plausible. And they did a great job. It's a brilliant story, brilliant series. Really enjoyed it. Won't spoil it by telling you how it ended, but I doubt there'll be a sequel, because it did end.
Okay.
And it did end well, I thought.
Right.
Okay, Simon.
What was it called again?
Dark Matter.
Dark Matter, okay.
Dark Matter. And I think it was on Netflix. Can't remember now. But, terrific series. Really enjoyed it. And just so, they could have, well, they did. It got so very confusingly complicated towards the end. But, that's what made it so interesting. Yeah. Thank you, Simon. And our next question coming up in a moment. Let's take a break from the show to tell you about our sponsor, Incogni, and I'll be giving you a special Space Nuts URL so you can get up to 60% off Incogni. But first, what's Incogni all about? It's a way of cleaning up your online presence and reducing the risk of your personal information being sold to unscrupulous people via the dark web or just via a hacker who's trying to fleece you or other people. It's also a great way to reduce spam emails and spam phone calls, reduce the risk of identity theft, which is big business these days. I think, most significantly, it greatly reduces your risk of being scammed. And that is just such a viral thing that's happening around the world at the moment. So how does all this work? Well, it's simple. All you have to do is sign up to Incogni, give them permission to act on your behalf, and they'll do the rest. They'll trawl the internet and remove your personal information from the web, the stuff that can be found on search engines, public websites, even private databases. It's all easily accessible, and let's face it, you're really going to be able to clean up the entire World Wide Web of your personal information by yourself. Right now, Incogni is offering a significant discount for Space Nuts listeners, up to 60% off, and that comes with a 30-day money-back guarantee. Just go to incogni.com/spacenuts. That's INCOGNI, incogni.com/spacenuts to find out more. And they have special prices for students and graduates as well. Make your personal information much harder to find online with Incogni. Check out all their plans today at incogni.com/spacenuts. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
And that's a moment. This one's from Isaac on the Gold. He's from Brisbane, actually, in Australia. Isaac is 9 years old. He said, I have two questions. How do black holes spin if they take up no space? And why does spin affect space? And his dad's got a question as well. My dad asks, how does gravity bend space and thus bend light travelling past it? Isaac in Brisbane, 9 years old. Great to hear from you, Isaac. Thanks for sending your questions in. Why do black holes spin? I think someone else asked a similar question recently.
We covered this not very long ago.
Yeah.
And so what you've got to think about is how black holes are formed. If you have a star which is more than 10 times the mass of the sun, something like that, gets to the end of its life, the nuclear propulsion system of the star stops, and so gravity takes over, and the star collapses, or its core collapses to become a black hole. So what you've got is a star that is going to be spinning. It will rotate because everything is rotating or evolving. And as it rotates, the spin will get faster because of the conservation of angular momentum. So spin is conserved. So even when the black hole becomes something that, as Isaac says, takes up no space, it's still spinning. Even though it is a single point, it's still spinning because it's the original star that collapsed to form it was spinning. So that spin gets imparted to the black hole.
So it's just inherited, basically.
Yes, that's right. It's a good way of putting it, an inherited spin. I think I've got that as well. Isaac's dad wants to know how gravity bends space. We all want to know that, actually.
Yeah.
Because it's what we know is how much it bends space. We do understand the mechanics of what happens when you put mass there. You can accurately predict just how and how much space will be bent. But why does it happen? It's the effect of gravity. That's the phenomenon we call gravity. And at that level, we really don't understand it very well.
Yeah, this is the thing. We know dark matter exists. We can't prove it yet. We know gravity exists, but we don't know much about how it exists in the way it exists and whether or not it's a subatomic particle called a graviton. We know a lot of things that exist, but we don't know much about why they exist and how they exist.
Yeah, I suppose what you could say is that we know extremely accurately, and this was, one of your answers to that last question. Relativity works like a dream. Everything is so precise, following the rules that Einstein laid out in 1915. So that describes gravity incredibly well, incredibly accurately, but it is still only a description of gravity. It's not an understanding of how gravity arises.
Yeah.
And so, yes, we still have big mysteries there.
Relatively speaking.
Indeed.
Yes. Thanks, Isaac. Great to hear from you. Please send us questions again. Always love to hear from our younger listeners. And finally, we have a question from our old mate, Rusty. I believe Rusty's from Donnybrook.
G'day, Fred and Andrew and all you space nuts. It's Rusty in Donnybrook, Western Australia. It seems to me that soon, and that may be in astronomical terms, we'll be able to harness the energy of space itself. We know there's a lot of energy in space. It has most of it if you look at the expanding universe and dark energy. But when we do harness the energy of space, we should be able to crank up 1G drives that allow us to go anywhere we like with a swap over halfway. So the first half of the voyage is accelerating at 1G and the second half is decelerating at 1G. A funny thing happens. The crew, to them, seem to be travelling faster than the speed of light, so that they would go to Andromeda under these circumstances in 30 crew years. So just wondering what, Fred and Andrew, what your priorities would be once we do develop this drive, both for the solar system and in the wider universe. Thank you.
Oh, Rusty, just put us right there in the middle of it. What would our priorities be? Over to you, Fred.
Well, I've kind of said this before, and it's something that almost, Rusty's almost hinted at by referring to a trip to Andromeda, the Andromeda Galaxy. The view of our own galaxy from the outside is what I'd really like to see. I'd love to know how close our models are.
Just to make sure you got the colour right.
The colour, how many spiral arms it's got, what...
Don't we know that?
No, not really. We think it's a 4-arm spiral, which is quite unusual. So, there's a bar across the middle, what we call a bar in the galaxy, not one you lean up against, but one that you, a bit like a rod or something like that, that's made of stars. And from each end of the bar, it looks as though there are 2 spiral arms that emerge. And that's based on mapping that we can do from the inside of the galaxy. But just imagine what it would look like if you're on the outside of it.
Yeah. Yeah, that's a great... Yeah, I never contemplated that, to be honest. I know you've mentioned it before. I'd probably go further. I'd probably like to sort of get right away from our, I suppose, galactic cluster and look at the whole thing. I mean, I don't know how to explain it, but I'd like to be able to have in my view Andromeda and the Milky Way and whatever else is in the vicinity. I'm assuming there are great voids between galaxy clusters.
Yeah.
And I'd like to get out into one of them, looking back at our galaxy cluster. I suppose that's what I'm saying. I think that would be fascinating, just to see it all in one picture.
Yes, that's so. I think we're the Milky Way and the Andromeda Galaxy are the 2 biggest members of what we call the local group, which is about 30 galaxies thereabouts. And the next biggest one is the Triangular Galaxy. And then there's lots of small stuff. But we're part of a bigger cluster. I think it's the Virgo cluster that we're part of. I'm shocking at not remembering that we're a little bit of that. It was certainly one of the bigger galaxy clusters we're part of as well. So you want to get right outside that and see what it looks like and be able to point to our Milky Way and say, that's home. That's home.
Yeah, I mean, that's probably very unexciting to most people. I'm sure others have thought, okay, well, if I could get a 1G drive, what I would do is this. Maybe they can let us know. But, if we could achieve 1G drive, it would make travel around the solar system pretty schmick, wouldn't it?
It would, yes. It's a nice concept because you do 2 things. You give your spacecraft a long period of constant acceleration, but if you make it 1G, then you've also provided your spacecraft with artificial gravity. So it means that everybody can stand upright on the bottom of the spacecraft as it's accelerating.
Yeah.
The end away from the end away from the pointy bit. The bottom of your capsule. The acceleration would mean that you were actually kept there at exactly the same weight as you have on Earth, and then if you switched it round to slow down at the other end of your trip, you'd have 1G also decelerating you. It's a really neat idea if ever it can be made to work.
Do you think it could work?
Yes, well, it could, but the main issue is sustaining it for a long period. That's why it's something that we haven't done yet.
Maybe ion drive engines
that
or...
sort of thing, that's right. Yeah. That's the kind of thing that people think of.
Yeah, could be interesting. Thank you, Rusty. As always, you pulled one out of the big black box. It's he's always got a bit of a curveball for us, has Rusty. Nice to hear from you. That is the end of this particular episode. If you would like to ask questions of Fred, by all means, go to our website, spacenutspodcast.com. Spacenuts.io is the other URL. They'll both take you to the same place. You just click on the AMA tab at the top, and when you go in there, it gives you the option to send us a text or audio question. If you've got a device with a microphone, it's as easy as saying, "Hi, I'm Fred from Sydney, and I want to know." And away you go.
Try that.
And if you're not named Fred, you can send us questions too. Just tell us who you are and where you're from. And we'd love to hear from you, especially if you've contemplated sending a question and you've been a bit reluctant. There are no dumb questions in astronomy and space science. So, yeah, please do get onto our website and send us some questions ASAP. We're done. Fred, thank you very much.
You're welcome. It's always a pleasure, Andrew, and we'll talk again soon.
We will, possibly in the next few days. Who knows? That's Professor Fred Watson, astronomer at large. Hugh in the studio is just being Hugh in the studio today. Actually, I think he's being the guy who picks up the kids from school, Hugh in the studio. And from me, Andrew Dunkley, thanks for your company. We'll catch you again real soon on another episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.